This video is going to look at lattice enthalpy and Born Haber cycles. So, first of all, what are Born Haber cycles? Why have they been sent to A-level chemistry students to make their life miserable? So, Born Haber cycles are just a type of enthalpy cycle, energy level diagram, Hess cycle, whatever you want to call it. So they are normally written in the way that we can see on the right-hand side, which is an energy level diagram. So as we go up the diagram, we got higher energy, and as we go down, it's lower in energy. And they're just using Hess's law. So this idea that the enthalpy change for the direct route is the same as an indirect route, or for any reaction, enthalpy change is the same no matter which route I take. They're just so like a complicated Hess cycle that just has more energy levels to it. But the good thing about Born Haber cycles is they are super predictable, because rather than normal Hess cycles, which could usually be about all kinds of different things, Born Haber cycles are only about the enthalpy changes associated with forming ionic compounds. And not only that, but they tend to only involve, at A level at least, ionic compounds where you have either you just have a metal ion and a simple non-metal ion. And what I mean by simple is things like fluoride, chloride, bromide, iodide, maybe oxide or sulfide, but we're limiting things to group 7 or group 6, and we're not talking about hydroxide, sulfate, nitrate, carbonate, etc., for reasons which should become clear as we go through the Born Haber cycle. So they look complicated, but actually, because they're quite predictable, we can have a method to solve them. So first of all, I actually want to go through all the different energy changes. If you're really rusty on your energy changes, I've got a separate video on enthalpy change definitions. I've also got a separate video on Hess cycles, so check those out. They're in my physical chemistry or my calculations playlist. I can't remember which one. So forming ionic compounds. Let's talk about maybe where some misconceptions are coming in and where we get confused about all the different energy changes. So here's an equation for the formation, enthalpy of formation. Okay, 1 mole of sodium chloride. So to form 1 mole of sodium chloride from the elements in the standard states, I start with sodium, which is a solid, and I have chlorine gas. React them together, make sodium chloride. Now at GCSE, we simplified this quite a lot, or rather what we focused on in GCSE and at the beginning of A-level is how do the ions form. So that's quite useful. It's very important to focus on that because it means we can predict, for example, that sodium chloride is NaCl. And the reason we can predict that is because sodium has 281 as its electron configuration, chlorine has 287, and so we know that sodium loses an electron to form Na+, chlorine gains an electron to form Cl-, and that means that the overall formula is NaCl. Now, when we drew those diagrams of the two ions, we would often also sometimes just like write those GCSE questions, you know, the ones that would say what happens when sodium reacts with chlorine, and we would just write, oh, sodium has 1 in its outer shell, so it loses an electron. Chlorine has 7 in its outer shell, so it gains 1 electron. We form a positive ion and a negative ion, and boom, we've got sodium chloride. Well, yeah, but when we draw sodium, so what we're drawing there is sodium gas. Sodium is not a gas, is it? So what we've drawn there is sodium atoms, but that's not how sodium is. So the only change we've shown there is the one that we cover right at the beginning of A-level, which is the first ionisation energy of sodium. So to get the first ionisation energy, to find out how much energy it takes to remove an electron, and it is an endothermic process, you have to turn sodium to a gas first, and it's not a gas, and no metals are gases under standard conditions. Similarly, not so familiar because we don't do it at the beginning of A level so much. This energy change here, so I could write an equation for this. It would be Na gas, and we'd have the electron on the other side. This I could write an equation, and again, I've gone from chlorine atoms, not chlorine molecules, and I'm adding an electron. And this is called my first electron affinity. So another thing to notice is that the word ionization in the context of energy changes always means forming a positive ion. That's the same actually for mass spec, okay? So actually when we talk about ionizing something, we mean that we're removing an electron because we have another name for adding an electron, even though they're both ions. Okay, so where am I going with this? You don't start the reaction to make sodium chloride with sodium gas and chlorine gas. You have sodium solid, which has metallic bonding. Okay, there are delocalized electrons. The electrons aren't in the outer shell. They're traveling freely through this lattice of positive ions and delocalized electrons. So we have another energy change to get from sodium solid to sodium gas, and that is what we call my delta H, enthalpy change of atomization. So in this case, we are breaking the metallic bonds in sodium in the lattice to form individual sodium atoms. We're putting those delocalized electrons back on the outer shell and forming a fairly unnatural state for sodium to be in. So with chlorine's already a gas, right? But it's not atoms. So none of the non-metals in any of these Born Haber cycles will start as atoms, because the only thing that starts as gas atoms is noble gases, and they're not going to be in a Born Haber cycle. So chlorine is a gas, but it's Cl2. So I have to atomize chlorine. And so that is the enthalpy change. Now, actually what I'm doing there is taking half a mole of Cl2 to make 1 mole of Cl atoms. So the definition of enthalpy change of atomization is to form 1 mole of atoms. So it's what I make, not what I start with. So for example, I can't start with 1 mole of chlorine because that's Cl2. I have to start with half a mole of chlorine molecules. So in that case, I'm breaking the bond. In some situations, like bromine, I might have, which is a liquid, I might have to turn it into a gas first and then break its bonds. But we just group it as one enthalpy change for the Born Haber cycle. So I start with sodium solid, chlorine gas. I've got to break whatever bonding is present in that element first. So I have to break metallic bonds in sodium to atomize it, break covalent bonds in chlorine to atomize it. Then I can remove the electron from the sodium atom and give it to the chlorine atom. So I've now made sodium ions and chloride ions. So have I made sodium chloride yet, which is the product of this reaction? No, I haven't. This is what I've got, gas ions. So in order to make sodium chloride's not a gas, it's a solid, and it's a solid because it has strong ionic bonds between all those oppositely charged ions. So as soon as I've made those ions, it'll be rather difficult to keep them apart. They are going to all stick together in a giant ionic lattice structure, and that is another energy change, and that is my lattice enthalpy. So in this direction from left to right, this is the normal direction that is used at A level. So it's enthalpy of lattice formation, but because many A-level syllabuses only cover the formation, they may just call it lattice enthalpy or even lattice energy because simply that's the only one that we cover. It's always exothermic because we are making very strong bonds between the ions. Okay, so they're all attracted to each other and they're coming together. So it's like when you make a covalent bond, you give energy out. It is in fact like the equivalent of our covalent bond enthalpy. So lattice enthalpy is a measure of the strength of the ionic bonding in an ionic compound, just like covalent bond enthalpy is a measure of the strength of a covalent bond. You can go the other way, and this is what would be called dissociation, lattice dissociation enthalpy, and that would be endothermic, so it would obviously be exactly the same number, but opposite sign, positive sign. So lattice formation is exothermic, should have a negative sign. It's very large, much larger than covalent bonds because it's not a single bond. We're talking about like a mole of lattice having attractions in all directions. And we start with the gaseous ions and we bring them together and it gives out energy. So before we just look at the Born Haber cycles, we do actually get questions asking us to compare lattice enthalpy between different ionic compounds. So lattice enthalpy is affected by what we call the charge density, and charge density is just about the charge on the ions. That could be the positive or the negative ion, so whether it's +1 or +2 or -1 or -2, and also the size of the ions or the ionic radius. And that is because the smaller the ion is, the closer it can get to other ions, and therefore the stronger the attraction between them. So if we look at the first two values on this table, just wanted to get an idea of like what's more important. Is it the charge or is it the size? Well, in the first two compounds, if we look at the thing that's changed, so chlorine is the same, this chloride ion, and Na plus and K plus both have the same charge. So we have the same charge, but K plus, potassium, is further down the periodic table, so has a greater ionic radius. Do be careful that you say ionic radius and not atomic, okay? Because at this point we formed the ionic compound, there are no atoms present. So that means there is a weaker attraction between the ions, because you can say there's less charge density, or you can say there's a bigger distance between the ions. To be honest, you can just say that K plus is a bigger ion and therefore weaker attraction. So if we look at that difference, be careful as well that you're saying attraction between ions and not attraction between the nucleus and the outer shell, because that's not relevant. We've already removed and added electrons. So the distance between the nucleus isn't relevant right now. It is the distance between the cations and the anions in the lattice. So there's not a big difference, 771, 701. All we've done is add one shell. The charge has stayed the same. If we then compared that with MgCl2 and NaCl, so these are in the same period. Sodium and magnesium are in the same period, but magnesium is 2+ and sodium is 1+. Now you can see a much bigger difference in the lattice enthalpy. We've gone from -771 to nearly 2,500. So charge makes a much bigger difference, and that makes sense when you think about it, because when I go from 1+ to 2+, I've literally doubled the charge. It's very difficult to double the size, like you have to add a lot of shells of electrons to double the size of an ion. So also the magnesium ion is smaller than sodium, so even though they're in the same period with the same number of shells, because of the extra proton in the nucleus, those electrons are pulled much closer. So it's also smaller. So we can just say, actually, join those together. The fact that it has a bigger charge and is smaller means it has a much greater charge density. So a lot more charge over a lot smaller volume of ion, meaning much stronger attractions. Now, sometimes we look at the Cl- and we're like, oh, but there's 2 chloride ions, so isn't that important as well? Because like there's more ionic bonds in magnesium chloride. Yeah, okay, we could say that there's 2 chloride ions, so that's contributing some of the difference, which is why I've also added Mgs. So Mg is 2+, and S is 2 minus. So there's only one sulfide ion. And then again, you can see another big increase, because remember these are exothermic values. So the lattice enthalpy has got much more exothermic. So actually I should say 2 minus. The fact that sulfide is a 2 minus, and I've deliberately picked elements that are all from the same period of the periodic table, means that it's far stronger attraction, even though there's only one S2 minus ion instead of 2 chloride ions. In fact, magnesium sulfide is probably getting to being less ionic than the others, but at the end of the video is when we will look at the difference as how we can tell from lattice enthalpy values whether something is actually becoming such a strong ionic bond or so different due to the charges that actually it becomes covalent. But we'll cover that at the end of the video. Let's get back to Born Haber cycles. So the outline, here's what we've got. This is one for just a very simple 1 plus 1 minus situation. And I want to see how we can apply this to Hess's law. So Hess's law tells us that we have like a direct route and an indirect route, and they're the same energy change. So this delta H formation of the compound, where we go from the elements to the solid ionic lattice, that is my direct route. So I can start, that's what it says, start here, and I can go direct from lithium solid and half a mole of fluorine gas to lithium fluoride solid, and that's my delta H formation. Route 2 is basically splitting all of the enthalpy changes that we talked about up and showing them as individual processes. So the first thing we do, remember, is we take the solid metal and we turn it into metal atoms. So we break the metallic bonds. So that's step 1. We atomize the lithium. The next thing we can do, and they're in different orders depending on Born Haber cycles. In this situation, what the thing they've done next, if I circle what's changed, we can see that should be it. There's a missing superscript there, but never mind. Lithium going to lithium plus and an electron. So that step there, let's label these steps. So the first step is delta H atomization of lithium. And the reason I know that is because I go from lithium solid to lithium gas. The next step is the first ionization energy of lithium. And that's because I've gone from lithium to lithium plus and an electron. Step number 3, I've gone from half a mole of F2, remember those covalent bonds. I've broken them and I've made 1 mole of fluorine atoms. So that is my delta H atomization of fluorine. Now all of those 3 changes are endothermic. So to atomize something, you're breaking metallic bonds or you're breaking covalent bonds. Definitely need to put in energy. To ionize something, you remove an electron. The electron is attracted to the nucleus, so I have to put in energy to take it away. Step 4 is our electron affinity. So this is the first electron affinity. Just like ionization energies, we call them first, second, third, because we can add more than 1 electron, just like we can take more than 1 away. That's the first electron affinity of fluorine. Now actually, fluorine has a space for that electron. It's attracting the electron. And so this is exothermic, and that's why the arrow is now going down. But it's still going in the same direction. So what I mean is we can follow that arrow. We're not swapping any arrows around right now. We're just doing all the steps we need to do to get to lithium fluoride. At this point, we're at that point where we've made lithium ions and fluoride ions. Again, sorry about the dodgy lack of plus and minus aren't in quite the right place there. We've made the ions, and then this is my lattice enthalpy, which is also exothermic, forming the lattice. So basically, in terms of the maths, route 1 is delta H formation, and that enthalpy change, whatever that is going to be equal to step 1 plus step 2 plus step 3 plus step 4 plus step 5. So you may have learned different ways to do this. You may also be looking at this and going, well, I can see that actually, you know, there's a square there and a square there, and what goes up must come down, and that's all fine. But this is a really foolproof way to answer any Born Haber cycle question, because it doesn't matter which step I'm trying to calculate, I can do it with every single one of these values. I can find the other values. Even when it becomes more complicated, even when there's two lots of something, I can still work it out. And I haven't changed the sign of anything. So step 4 and step 5 are negative values, but I don't need to do anything with them. I'm just adding them up. So let's put this to some examples. We're now going to go straight to a 2 plus 1 minus. So group 2, group 7 compound is actually the most common type of lattice energy question that you're going to get. And so we're going to show how we put all the different values in and how we build up. You don't normally have to write your whole own Born Haber cycle. These days you usually just have to add bits in, but if you can do it from scratch, that means you can add any of the parts. So bottom left hand corner is going to be my delta H formation. So I'm going to have magnesium solid plus Cl2, which is a gas. And then that arrow is showing, so remember these arrows are just reaction arrows, right? So that makes MgCl2 solid. And that arrow represents enthalpy change of formation of magnesium chloride from elements to compound standard state. So that is minus 642. Then I'm just going to go up, and remember I'm going to tick off the values I've used. It doesn't matter which order we do these in, just by convention we usually go atomization metal, atomization non-metal, and then we make the ions. So I am going to atomize my magnesium first. You don't have to. You could atomize the chlorine first. So the change that happens is I go magnesium solid to magnesium gas. I've not changed my chlorine. I need to still write it in because otherwise it's not balanced. So that arrow from solid to gas is equal to 150 plus 150. Now I'm going to atomize my chlorine, but there are 2 chlorine atoms in a molecule, and I'm going to need 2 chlorine atoms to make MgCl2. So that value there is for individual 1 mole of atoms, and I want to make 2 moles. So I'm going to do plus 121 times 2. And that means I'm going to make 2 Cl gas. So remember the difference, Cl2 sharing electrons, a molecule, 2 Cls. I've now made those atoms, 287. Next thing that I need to do is ionize my magnesium. There are 2 enthalpy changes for that because I need to remove 1 electron and then the second. So if I'm showing them individually, it would be Mg plus. Remember, if we had an equation that said write the first ionization energy, you'd go Mg gas goes to Mg plus an electron, and I have 2 Cls because I haven't done anything with those in that step. So this one is equal to plus 736. Then we remove the second electron from magnesium, so it becomes Mg2 plus. So now I have 2 electrons lying around, one from the first ionization and one from the second, and I've got my 2 chlorine atoms ready to receive, and that one is plus 1450. And expect in exam questions to be asked about ionization energies. You learned about it right in one of the very early topics on atomic structure. It will come up again, like why is that more endothermic? The second one, I'm removing it from a positive ion, so there's a stronger attraction. Then we come down, because now when we add an electron to an atom, that is an exothermic change because the electron is attracted to the chlorine, but there are 2 of them. So it's going to be minus 364 times 2 for my electron affinity. So the difference, first plus second, means I take one atom, I take the first electron, then I take the second. First electron affinity, I'm only adding one electron, but I'm adding it to 2 chlorine atoms, so I'm going to do it twice, or 2 moles of chlorine atoms. And then what I've got, what I should have in this right-hand corner is basically all my ions ready to come together and make my solid. So this is my lattice enthalpy, and that's the thing that I'm trying to find. It isn't always the thing that we're trying to find, so we're going to do examples where we find other things. Right, so what did we say? This is the directory. All the other values added together equal that. So I'm going to write my maths out in that form. So what do I mean by that? Minus 642, I'm going to put that on one side of the equals sign. And then I'm just going to put all the other arrows in order. Plus 150 plus, well, 121 times 2 is 242, and that's positive, plus 736, and that's positive, plus 1450, and that's positive. Now I'm going down the other side. It's a negative sign, but I'm still adding it, as in I'm not changing the direction of the arrow. So 364 times 2 is 728, but it's negative. So it's plus minus 728. And then plus lattice enthalpy. That's the thing I'm trying to find. So those 1, 2, 3, 4, 5, 6 different values are all added together, and they will equal minus 642. Now you could now take every single one of those values to the other side and write minus 642, minus 150, minus 242, minus 736, minus 1450, plus, minus, minus, you know what I mean? Like, don't do that. Add all this up before you move it. It's just a lot more foolproof. If you add all that up and then take it away from the other side, it's just a lot easier than trying to take everything away like lots of times. So I'm going to add all of that up, and what I get is minus 642 equals 1850. So that's what I get when I add all those values, including the negative value for the electron affinity, plus lattice enthalpy, which means that minus 642 minus 1850, because I'm taking it to the other side, equals minus 2492, and that is my lattice enthalpy in kilojoules per mole. Foolproof method. Let's show it again for finding a different value. So this is a situation where the Born Haber cycle looks slightly different, and I've got some labels to fill in. So when you're filling in labels, again, remember that there is a set format here. So this is my delta H formation, going from calcium solid to bromine liquid, elements in standard state, making compound CaBr2, and that will be a solid. All ionic compounds are solids. Then there's a slightly different situation. So A, we're atomizing, so I'm going to put in some numbers as well because I actually know some numbers. So this is minus 683. The point of this question, incidentally, is to find the one that I don't know. So let's find the one that I don't know. Calcium solid going to calcium gas. Atomization plus 178. That's done. Now the next thing that's happening is I am changing something about the bromine, and I can tell because there's a space here. So I'm atomizing bromine. I've got Br2, so I'm going to make 2 moles of bromine atoms, which will now be gas. So there's 2 changes happening there. We're breaking the bond, we're turning it into a gas. We're breaking 1 mole of bonds, but we're forming 2 moles of atoms. So I need to take this value here and times it by 2, 224. 4. Okay, now actually calcium is a 2+ ion, so C is 2 enthalpy changes together, because I have to do plus 590 and then I have to take away the second electron to get to plus 1145. And I know it's those because I've gone from Ca to Ca2+. So that's how I know that that goes there. There must be 2 electrons. That's the bit that doesn't have a state symbol. And then the 2Br is exactly as it was before. I haven't changed that. And I also know that because that's the endothermic bit and D is the exothermic bit. And D I don't have. So the values that I've used, that one, that one, that one, that one, and that one, the one I've got left is this one, and that's E, minus 2176. Lattice enthalpy of formation from the ions to the ionic compound at the bottom. So D, this question was actually asking to find the first electron affinity of bromine. And it is correct to write Br here rather than Br2 because we are actually talking about individual gaseous atoms. Right, okay, so we are going to use exactly the same strategy as we did before. Lattice enthalpy is the direct route. Sorry, not lattice. The formation enthalpy is the direct route. Equals plus 178 plus 224 plus 590 plus 1145 plus D plus minus 2176. You don't really need the brackets, but I just like to show that we're just adding all these numbers, and if they're negative, we're still adding them, okay, because it's still going all the way around, following the arrows from one thing to another. I haven't changed the direction of any arrows. Okay, like we did before, I'm going to sort of put D on its own and work everything else out. So minus 683, if I put all of the other stuff, 178, 224, 590, 1145, and minus 2176, I will get minus 39. It's a bit of an anticlimax, but because they almost all cancel out. Plus D. So minus 683 plus 39, or you can say minus 39, equals what D is, and that's minus 644. And then we need to be careful because the question is actually asking not what is arrow D, but what is the value for the first electron affinity of bromine. Well, this is 2 times the first electron affinity because I've got 2 atoms of bromine. So if I want to find that, I have to take that minus 644 divided by 2 is minus 322 is my answer. And that's a really common thing, asking you to find electron affinity for something where there's 2 atoms and 2 negative ions in the compound. So 2 plus 1 minus ions, practice those a lot, they're very common. You could also get a 1 plus 2 minus. So for example, potassium oxide. So let's do that and look at how the Born Haber cycle looks a bit different. So similarities, obviously you're going to start with your elements, 2 lots of potassium solid, half O2. So I only want 1 oxygen atom down here in my compound. So I only want half a mole of oxygen gas. So basically the main way that this is different is that I've got, in the previous examples, I had 1 mole of my metal and 2 moles of non-metal atoms. Here I have 1 mole of non-metal atoms and 2 moles of metal atoms. So it just means for my enthalpy changes, I've got to pay attention. I know that this bottom arrow is minus 362. That is enthalpy of formation of potassium oxide. Then I'm going from the top. Enthalpy of atomization is plus 90 for potassium, but there's 2 of them. So this value would be 2 lots of potassium going from solid to gas. And again, these could be written in the other way round, like you could atomize the oxygen first. It makes no difference to the calculation. I'm now going to atomize oxygen, and that is plus 248 because I only want to make 1 mole of oxygen atoms, 2K gas. Then I'm going to ionize my potassium. I need first ionization energy, which is 418, but I need 2 lots. So just like with the chlorine or the bromine, I had 2 lots of electron affinity. Here I've just got 2 lots of first ionization energy. And then this is the second place where it's different. So I am making a 2- ion, which means that I need a first electron affinity and a second. Now with ionization energy, they both went up. You had your first ionization energy and a second. So for something like calcium or magnesium, the second ionization energy was always bigger because it's harder to remove the second electron, but it was still endothermic. With electron affinity, it's a bit different. When you first add an electron, that's this value here, -142. So that's exothermic. It's not really big, but it's a little bit exothermic. And that is because, like we said, we are bringing together 2 things which are attracted, an electron and an atom that has a nucleus with positive charge that is pulling the electron towards it. But in the second electron affinity, what I'm doing is this process, taking a negative ion, adding another electron to make the O2-. Now that is actually quite endothermic. It's actually more endothermic than trying to take an electron away from potassium because you're overcoming a lot of repulsion. So that value then goes up. It just means that the Born Haber cycle looks a bit different in shape. Instead of a nice, neat going straight up, straight up, coming down, instead we have this going up, coming down, going up, and then back we go. So and then I'm just going to change the arrow on this side because normally this is the thing I was talking about before where lattice enthalpy can be defined in either direction. So if it's going up, that would be breaking the lattice apart. I'm just going to change my arrow so it's going down. And we're going to find lattice enthalpy as the exothermic value because that's the standard. So even though we're going up and down, can you see that we still got this route and this route? It's a bit more wobbly, it goes up and down, undulating if you like, but it's still following the arrows. So I can put it all in. I can put all my values in. -362 is the enthalpy of formation. That is equal to everything else. Plus 180, plus 248, plus 2 times 418, minus or plus -142 if we want to keep that same standard, plus 844, plus lattice enthalpy. Add up everything on that right hand side, work it all out, so it actually ends up being 1966 as all of those things added together and for lattice energy. So -362 take away 1966 equals lattice energy, and that equals -2328, which seems like a sensible value. So the value should be negative, and it's usually in thousands, like 1 or 2,000, maybe up to 3 if it's a really small ions with strong charge. So no matter what example you get with Born Haber cycles, they can look weird. So I thought I'd include some weird ones. Okay, they still have all of those enthalpy changes. So this is a weird one because delta H formation is actually like going up and to the right, but it's still going to go from elements to compounds. So there's my compound. So I'd still just have lithium solid and half, this is iodide, not fluoride, half a mole of iodine, and that would be a solid. You do need to know your states of halogens. You need to know that anyway. And then what it's done is done like parallel lines. So it's done the metal on the left and then the non-metal. So this would be delta H atomization of fluorine. So that would make fluorine. Oh gosh, I'm really obsessed with fluorine. Iodine. And that would make 1 iodine atom. And then we've got, don't worry about these symbols, you wouldn't get them looking like that. That's just ionization. And then that's just electron affinity. And they'd just be gases. So it's all the same energy changes. It's all in the same order. We've just put some next to each other. And you've seen that before, because sometimes in a, for example, Hess cycle, if you had elements down here, and then let's say that you had CaCO3 and CaO plus CO2, then you would have two lots of delta H formation on that array, right? So you can have one array that represents two things. Also, like some of these are exothermic and some of these are endothermic, and it's not an energy level diagram, it's just a triangle. And that's what they've done there. So you can show it as a Hess cycle rather than as an energy level diagram. It does not have to go up and come back down. Other examples, therefore, this is just one where it does go up and it does come down where I'm expecting it to, but not necessarily, because here I've got both. I'm basically doing all of the ionizing. So there's a whole lot of work on that one array. That one array would be first ionization energy and second ionization energy for calcium, and two lots of the first electron affinity for chlorine. So there's like 3 energy changes on that array. But there's this one on the right is just lattice enthalpy. So you can just put it together from what you're making and knowing your definitions. And then, again, weird diagonal things going on. Same idea as the one on the right hand side of this slide, actually. It's simply just been drawn slightly differently. So for example, down here, that's just delta H formation. Solid, gas, standard states, compound. So look at what's on either side of the arrows and you should be able to label anything, even if it's weirdly arranged. Okay, in this marathon video, the next thing I'm going to look at, this is only applicable if you are doing Edexcel or AQA, and I think also CIE. Okay, so basically if you're doing OCR, you do not need to know about this thing about lattice enthalpy. So experimental versus theoretical lattice enthalpy. What is that about? So biggest thing that you need to realize is that experimental in this context means from the Born Haber cycle that we were just doing. Yeah, it's not an experiment. It's nowhere near as fun as doing an experiment. It feels nothing like doing an experiment. It's highly theoretical when we do it. However, all those values that we just took, the atomization, the ionization, the electron affinity, the enthalpy of formation, they were all calculated from experiments. We may have had to use Hess's law, we may have had to do indirect stuff, but they were all true measures of the actual bonding that's going on in those compounds. So, experimental, the values on the right-hand side of this table came from real, true, as close as we can get them, accurate values from, people who are generally better at doing these experiments than sixth form students. Theoretical means put it in a computer. And what the theoretical value does is just go, well, it's an ionic compound. I can take a magnesium ion. I know how big it is, like that is from an experiment. I know how, like, the radius. And I also know all of the charges inside it, how they're distributed. So you can get an idea like the charge density, for example. Magnesium is a 2+. Now that is a relative charge. We could actually put a value in coulombs on that. We could put a value of the radius in nanometers. We could work out the volume over which those coulombs of charge are spread. And what we could actually do is work out the force of attraction between the ions and how they're arranged in the lattice. So a computer can do that. And what it's assuming is that everything is just as we'd expect in that picture there. A perfect ionic lattice with perfect spheres of charge which are attracted to each other and get as close as they can, etc. So why do we compare the two values? Well, I've given you 2 examples of compounds here. And what you can see is that for the second compound, barium iodide, these values are close together. They're very similar. So what that's telling me is that barium iodide is a typical ionic compound with a lot of clearly ionic tendency. Like basically it looks like that picture that we've got on the left hand side. The electrons get transferred, the negative ions are minding their business, being spherical, and so are the positive ions. But when I look at magnesium iodide, there is a much bigger discrepancy. And we can see that the true value, the experimental value, is more exothermic, suggesting there's something different about the bonding that cannot be explained simply by saying that magnesium iodide is perfect spheres of ionic charge. So when we get that really big difference between the values, and we're not looking at these two values, okay? So if I was comparing these two, actually no, let's compare these two values here, the real values. If I was just comparing the real values between barium iodide and magnesium iodide, we just go back to what we did earlier. Barium is further down the group, which means it has more shells, greater ionic radius, so it's just a weaker attraction between the ions. That's why there is this minus 1,800 instead of minus 2,300. But now we're looking at this difference and we're trying to explain that. So if it's more exothermic, it actually means it's less ionic than we think. Covalent bonds are the strongest type of bonds that we know. That's why diamond is the hardest, strongest melting point substance. So if it's more exothermic, it actually means we have something called covalent character. Now, what happens in covalent bonding is sharing instead of an ionic lattice. It's not completely covalent. If it was completely covalent, it'd be a molecule, right? And it would be a gas at room temperature, so it's definitely not that. So why is this happening? Magnesium is smaller than barium, and it is also a high positive charge, so it has a high charge density. So it really pulls electrons towards it very strongly. Iodide is a negative charge. It's a really big ion. Like, it's got 58 electrons. That's a lot. No, 54, miscounted. So I minus, instead of being this nice circle right next to the magnesium, what happens is the negative charge on the iodide, instead of being all around the outer shell of the iodide, is getting pulled towards the magnesium. The more that it's doing that, can you see the more it gets closer to being shared rather than simply being on one ion? And so how we describe that is we say that Mg2+ polarizes or distorts the I- ion. So this is always an effect that the cation has on the anion. The anion can't pull electrons towards it. It's just holding on to the electrons it's already got. Only positive ions can polarize. The I- ion, because it's a large negative ion, means it's very polarizable. So the bigger the negative ion and the smaller the positive ion, the bigger this effect will be and the more covalent character you will have. The bigger the charge on either of them, the more covalent character. And the reason for that is if you have a high positive charge, you're going to pull things towards it. If you have a high negative charge, it's harder for the negative ion to actually hold on to its electrons. And so also you're going to have a more polarizable anion as well. So we only bring this up if we're comparing theoretical and experimental. We don't bring this up if we're just comparing two compounds like we're comparing magnesium iodide and barium iodide. If we're just doing that, we just go back to magnesium's a smaller ion, so it's got stronger attractions. That's all we need to do. So high, small, positively charged ions with big negative anions means we're going to tend towards pulling the electrons back and getting slightly more like a covalent bond, but it's not actually covalent because it's not going to make a molecule. Some compounds like aluminium chloride actually go all the way into forming covalent bonds because aluminium is so positive and small that it's actually able to completely pull the electrons back, and they end up sharing instead.